So let's start. Hi everyone, and welcome to this talk about paradigms of applied machine learning from. My name is Dmitrii. I'm a machine learning engineer at Meta. I'm speaking for my employer today. I'm working on machine learning powered systems for the last decade or so, and I have experience both traditional industries and internets. So today we're going to talk about different of machine learning applications and how it influences systems behind different applications. Introduce what kind of systems we are talking about overall, what kind of problems we solve with machine learning systems. Second, we're going to talk about how this is used in traditional enterprises. Then we'll talk about more like modern recommendation systems for internet scale services, and we'll wrap up with new like cutting-edge stuff about generative AI. I'll leave some time for questions after the last like the last three sections. So feel free to use Q&A feature of this. I'm going to read question from here. Yeah, I'm going to share the slides as well. I'll send you a link. So let's get started. Introduction into machine learning. I copied this quote from Wikipedia. And what is like machine learning code, and I highlighted pieces which are important for system perspective. So first and foremost, when we're talking about applications of machine learning, we are talking about some specific tasks which we want computer to perform. We're not talking about like general intelligence or anything like this. It's something we want computer to do. And second, we want to improve how computer does this. So it means we typically without machine learning in some way, maybe in very bad, not super efficiently, but we apply machine learning that could be solved in some other way. And third, to apply machine learning, we leverage data. So machine learning is an approach where we learn from data and use this learnings to perform tasks. So how does it translate into system concerns? The problem is like both good thing and bad thing, because when we add data, we add a lot of unknowns and a lot of new kind of parameters, new states of the system. And it's very easy to make a mess if you put bad data in, you get bad answers out. And a lot of work from system side is to make it less probable, not impossible, but less probable, make our systems bulletproof, make our applications tolerant to faults in data, or at least like able to detect and remediate the faults. Specifically, we handle such stages of machine learning applications as training data collection and preparation, features definition and computation, orchestration of training the models, and managing trained models, doing inference of using these models, and also measuring and evaluating how the model performs. If you don't know some of the words here, don't worry. We'll talk about this in more detail going forward. So, sorry, I see there are some problems with my sound. Sorry about this. Is it better now?
Yes.
Okay, I hope it's better. Okay, let's go ahead. Machine learning in traditional enterprises. So let's start with some examples. What is considered like traditional enterprises? It's scientific definition, obviously, would define as like some businesses which operate in large part in real world, not in the internet. So like financial industry, insurance companies, retail, something like this. So for this kind of businesses, what we want to do is predict probabilities of different events, or predict like some numbers, category like some scenario in the future, typically relate to money. So we can predict probability of default on a loan. We can predict probability of insurance claim by some specific customer, or we predict future like value of revenue streams in terms of like investments, or in terms of revenue coming from some retail store, things like this. Do you hear me well now? Does it work? I'm not sure I can make it better, to be honest. Let me just talk a bit louder. So, going forward, what are the constraints to operate in this scenario? First is like train is relatively small, which means models are relatively small. And the cause of this basically is long feedback loop. So when you do some prediction, you do something in the real world, you need to wait for some time to like observe concepts of yours. Therefore, models are updated not very frequently. Therefore, it's important to handle like temporal aspects of modeling over long time horizon. So like your model should perform both during Black Friday and during like low season of sales, for example. Then another consequences is that quality of the prediction is evaluated more time. It's hard to evaluate anything inference time because of this feedback. Just no way to evaluate it objectively. And this leads to this training versus inference mismatch problem, which we'll talk about in the later. Also, sometimes explainability tends to be more important. It's less systems, more about modeling, but I should mention this. So that doing things like insurance claims prediction or loan prediction, you want your decisions to be explainable for legal reasons. And if you want this, your bet is linear models, because linear models typically easy to explain. You have specific features, you have like specific weights of the features, you can assess how a model is going to make decision by looking at how it's implemented. Otherwise, if you don't want explainability, you can boost the decision trees, which would tend to provide optimal performance of these sizes of training data. Okay, let's talk about systems. So training data size is consideration for systems because you don't need to handle large data there here. And same for model sizes. On the other hand, at inference side, you by all means can do work with large data because your features might exist like in mouse and like inference examples might have a lot of inference examples, and you could do this inference offline in large batches. So you can do it online per request. These features you can calculate offline. You can sometimes calculate online. So in this case, it's like rather more rare. And you can also supply some features as like requests. For example, when you come for a loan, you can say how much you earn, and this is going to be like considered as part of your application. Okay, some questions. Let me address after I finish with this section. We can talk about like overall part. Let's go ahead. So I would say the biggest, most important component of machine learning infrastructure for traditional cases is feature store. What is feature store? It's a piece of technology which operates on some data from various sources and makes this data available for model training scenario and model serving or inference scenario. So you as on this like XKCD picture, you put in some data, you get out some data. Same in terms of systems. And responsibilities are following. So first, you want to have a registry of all features available, and you want to like define new features, keep track of your features. Then you want to provide access for to these features via serving pass or via training data preparation pass. Let's talk about each in turn. So features registry is basically a piece of software which keeps track of like features, maps feature ID to its definition. And definition involves physical data allocation. It can involve some transformations to define like derived features from some base features. In advanced cases, it defines also rules of computation on streaming data. For example, we can have like some features in specific table, ratios like age and table customers. You can have some feature which like ratio of two other features, and you can have some feature which is supplied only during like inference requests or in data. So you want to assess something for application. Application has a postcode. You don't know this postcode has this request. And this is less mature piece of like the stack. A lot of platforms provide this. For example, Amazon SageMaker, feature store with like nice interface. Even non-technical users could like use. This is mostly about metadata. Serving is more complicated. In the scenario we computed and stored in some table, in which case feature storing component is responsible for providing low latency access during request. So we utilize some like low key value storage or something like this in database in large. And batch access is typically necessary for the training data preparation. It's interesting how derived features could be handled either on the fly using some kind of API wrapper when you make like this API does it from, or they could be pre-computed, and there is a trade-off between complexity and compute cost in the former case versus storage space in the latter case. If you have combinations of derived features, probably won't be able to store them in database. Then training preparations, even more complicated. Like some cases, let's say. First of all, it's like rarely automated as regular process. It's mostly done when data is available. So in simplest cases, it could be done in hoc manner by data scientists. When you don't have any platform, you have just like database and a table. you can build machine learning model over this table. But if you have like machine learning, you would utilize a feature registry to provide access to training data. Important concern here is temporal aspects of data, as we discussed before. You want to look up historical data. If you train over like 1 year of data, you need to join with 1 year of data. This is extremely. Also, you don't want to use data from the future, otherwise your model will perform like really bad. Okay, I'll turn off my video. Sorry about this. Going forward, we have an example. So for training data preparation on Databricks platform, there is a specific API. They operate over like tables and columns, as they provide this kind of big data flavored solution. And you have like names, columns in the table. You also have a lookup key by which to join, and then you join your training data set with these tables to training set with both features and your like prediction, such as rating in this. So that's all good. There's a problem, which is called training mismatch. And the problem is that training data distribution could change since you trained your model. So for example, if you use feature such as price and pricing policy was changed, then model doesn't know how to handle it typically. It would be confused why like prices are bigger and won't give you right predictions. It also could happen for technical reasons. Something could break in your data and like you get bad inputs and provide bad outputs. So in case of non-technical issues, we can remediate it partially by making features themselves resistant to such effects. So you can normalize, for example, prices by average price, and this normalized price won't be changed, even if pricing policy has changed in certain ways. But it is not always feasible, not always desirable. Sometimes you want to use like your absolute values. So another remediation is like retraining model frequently. Obviously, you can do this. If you can do this, if you cannot. So like middle ground here is like monitoring of this problem. So if you cannot model frequently, you can monitor from the situation, and when you see the situation occurring, when some features very different data distribution or predictions themselves have very different data distribution compared to what I observed at training, you can have more urgency with retraining, collecting retraining data, etc. So far, so good. I think this is here is model management. So you have your features, you trained your model. Now, in cases you have like many such models, so you create new models frequently, like create new versions of models. You want to have some like layer for model management. So you want to standardize like how you store your models. You want to like have ability for safe rollout of new versions, like roll out new version only to part of customers or part of like requests, and observe how it performs before you replace it fully. Metadata management as well. You like as data scientist, you want to like track how different models performed over time, like stuff like this. And from engineering perspective, one interesting piece here is like feature deprecation. So if you have some feature which you want to delete, you want to know which models are using this feature. So having some standardized model management approach really helps with this. And a big like companies, big deployments of machine learning technologies, you use this a lot. Such system is MLflow by Databricks. It's also available as open source, but also as part of their platform, which basically does what I described before. And last but not least, model inference. Somewhat similar to feature serving. You can do it on online mode. And considerations are really similar. So won't go to details here. I think we are done with traditional cases, and I'm happy to answer your questions. So first one, what is daily work run among both linear and tree? I think it's not about like some specific number universally, right? Because length, like you apply linear models when they work. When they don't work, like more complicated models. And you also apply linear models when you have to apply them, when you need explainability, which trees are not very good with. So yeah, I mean, in my experience, we started like at some company where we started with like a lot of linear models and slowly migrated to decision trees because they performed better and we didn't need a lot of like explainability. But yeah, if you like insurance company and you're making decisions, probably will stick with linear models. Explanation. Yeah, good point. So data lineage is basic ability to understand where your data come from. So you have a feature is defined using some data tables. For example, we had some case where we had like drive such as total spend divided by number of users. These two features could come from different tables. So your lineage is that you have a specific model which uses your average price feature, and then your feature uses some two other features, and you have two columns behind this feature. And suppose you want to create column behind number of purchases because it's not, for example, when you have like new column this data. How do you know which models are using this column? Which models are dependent on, so that if you deprecate it, you won't break anything. This is your like, data lineage problem. It's not really specific to machine learning. It occurs a lot like in data warehouse scenarios, like overall. So yeah. Okay, if no more questions on this, let's go to recommendation systems, which is a bit more interesting. So I'm talking about scenarios such as algorithmic feed. So you have some kind of feed of content and you want to rank or sort it for users from like most relevant to least relevant and show only most relevant content. Content in this case could be literally anything. It could be search results, posts, ads, like hotels, even transport routes, like when you query Google, like build your road from like home to work. You really what you do is you rank several roads according to some criteria. And this kind of problem typically involves optimizations of multiple objectives. So you have different kind of events happening in the real world, and you can predict and use combination of these events to define like the most relevant, make definition of the most relevant content. So in case of, I don't know, social network, you have like probability of clicking on a post, on sharing of a post, or a post may be ad. So like this is completely different scenario whether user is going to click on a specific ad, whether they're interested in buying something. Or if a post is a video, you can have like time spent watching this video and so on. So what you do is you combine this prediction in some kind of total score using some intuitions about how like importance of these terms are relative to each other. and then you sort accordingly. This is what we are going to talk here. So what are the constraints and challenges of this scenario? First of all, much more data and much bigger models, therefore, like be able to make use of this data, which creates new like technical challenges for us as engineers. Second, really short feedback loop. So if you predict where the user is good and you show them this ad, you'll know whether they clicked or not right away. So this means that models could be updated really frequently and also automatically, because you collect this data automatically. This also means that your system would benefit a lot from real-time features, because you have like this fast feedback loop, and you can personalize predictions for your user like according to their most recent actions. And last, really important, is that it's possible to A/B test your changes. It's like becomes ultimate performance evaluation tool. You can compare how your old model performs versus new model by applying this model to different groups. About this in detail. The kind of conclusion here is that it becomes much more objective, much easier to iterate on and improve. And this needs to be supported by systems. Another problem, kind of challenge here, is data distribution drift. Similar to what we are talking about, like outdated features in previous scenario, but here it could happen even like more frequently, because if pricing strategy could change like once a year or twice a year, but users' interests could change every day. So models not only could but should update it really frequently and automatically. Otherwise, your system won't be very good. So let's see how it works in practice with specific systems. So considering all of this, as I described, training data is generated within the self, so we can have this feedback loop of model performance. But on the other hand, models are expensive to train, right? So you have a lot of data to train a model on a lot of data. You need a lot of compute power, which is not always available. So there is something called incremental training, which is possible. I will describe it on one of the next slides. Also, online inference is really the only option here. You cannot do batch inference, because if you make your predictions based on batch inference, it would be not very high quality and outdated. It would be outdated really quickly. You want to incorporate the most recent signals from your users. One specific case online like inference is something called event-based features. I will describe what it is, how it applies to these systems. And then I mentioned A/B testing also as well, and multi-stage ranking for system efficiency is some like smart optimization I would describe. Okay, let's go. Training data management. It's technically much more complicated in this case, but also much more useful. When in previous scenario, you like given some training data and you only can like use it or not use it, or maybe you can clean it up a bit, maybe you validate it a bit, but not a lot of freedom what you can do. Here, basically what you have is like log of use. You make some predictions using some features, and users act on this prediction. What you can do is you can prepare training data straight away, and you can continue to train your models. So training data management kind of boils down to ability to collect the data efficiently at scale, and reliably, because retraining of the model is like crucial piece of your stack of technology. This monolith paper by ByteDance. I really encourage you to read it if you are interested in this topic. It basically describes like reference implementation of recommendation system. And yeah, incremental training. Basically, you collect an example using feedback from your system, and you do training straight away. You fit it into training system. You retrain your model. You start serving your model straight away. So this is kind of feedback loop which you have here, and more like quick you react with retraining, quick you like get better performance. Okay, I talked a lot about like onlineness and short feedback loops, and one of like representations of this scenario is sparse features. So in previous scenarios, in like a traditional like enterprise scenario, we had things like, I don't know, how many purchases customer made, or how many, I don't know, how expensive are those purchases. We can quickly accumulate a lot of specific like purchases customer made, or which specific posts customer liked them, and this is treated as a feature itself. So like feature is a list of these IDs of these posts or of these purchases. But the problem is, how do you input this into a model? Because this kind of variable sized input, right? You have like one might have like dozen of posts, another might have used like 100 of posts. How do you input into this? Is this into a machine learning model? Also, this like space of these possible values for this kind of IDs is millions or billions. You can have a lot of content in your system, which is another challenge for preparing it to be useful for a model. The solution here is feature embeddings. This is something which allows you to turn sparse features, this list of IDs, into fixed size, or we can call it dense set of numbers, or mathematically it's a vector. Let's take a look at this in detail. So this diagram, we have some kind of neural network, and the point here is these embeddings are kind of part of the network. So for each category, for each post ID, let's say, you have some vector, and you train these parameters of this vector as you train any other parameters of the model using the backpropagation. So the line between like features and model is becoming more blurry, because now you have some features which are trained together with the model. This is really interesting. And in terms of system constraints, we need to maintain some map, right? We have this post IDs, and we need to keep this embedding somewhere. And feature store now doesn't really all representations, the embeddings now it owns only like sparse representations. And at inference time, like model now like somehow pulls these embeddings there, typically like as a sum or something like this. So technically, the challenges here are like keeping these embeddings up to date in your post, and you post, or like embedding for a liked post should be different than you did this, right? But also you don't want to track it for like each and every ID. Posts are really rarely liked, whatever. You don't want to keep track of them, otherwise you have like too much to handle this efficiently. Also, if we like implement this map of embeddings as a hash map, you can have hash conflicts. You need to resolve it somehow. And overall, all the distributed system challenges together. Like you have, you need to handle updates. You need to handle read paths. You need to make tolerant. So like using some piece of hardware won't break it completely. Therefore, it's not really about machine learning now in large. It's a lot about distributed systems. That's what I would conclude here. So multi-stage ranking. This is about efficiency. So suppose you have like, I don't know, Twitter, have millions of tweets produced every day, maybe even billions, I don't know. That's certainly like dozens of millions is easy. And it's not feasible to rank them for every user. When you open Twitter, you can't expect like all the tweets to be ranked for you. So it would just take too much power, too much compute, too much like electricity in the end, right? So the solution here is to have something more of a retrieval stage. And it's typically some simpler model which is used to cheaply like scan these, I don't know, million items and find a smaller subset of items to rank. And in this model, typically you can, similar to this embeddings idea, compute some dense representations for your users or for your media or both, and then do some highly optimized comparison between these vectors. For example, you can do some clustering. You can pre-cluster like vectors which are close, and then you can online when you like do this ranking for specific user, you can rank only items in the cluster. So I would probably conclude here that modeling itself is like a problem as machine learning data, or that is data science problem, because how your like model is structured is defined not only by your, say, like business considerations, right, but also by technical consideration in large sense. You cannot solve these like large scale problems without like shaping your models in a way that would be efficient, that would utilize like data in real-time fashion and so on. So role of engineering here is arguably bigger than previous scenario. And but also this gives a lot of freedom, a lot of like freedom to iterate to the users in form of A/B testing. Sorry about this. Offline evaluation, as usual, like you can retrain your model, you can build new model, you can collect some metrics offline and find the best model. And if it's successful, instead of just rolling out your model to all users, you do A/B test. So you run your model on some subset of users for like a week, and you get some real-time feedback about how it influences business objective metrics. And you roll out your model only if business objective metrics are really good. For example, like if users time with your like recommendations because they're really good, this is kind of success scenario. If they spend less time, this might be something you don't want, you won't want to do. So there's like proliferation of these A/B testing systems as well. AWS, for example, provides some implementation, and more or less every platform provides an implementation for this. Yeah, I think this is all for recommendation systems. I'm happy to check the questions. So we have an example of recommendation system with other topics like advisors, recommendations. No, unfortunately, in case of recommendation systems, my experience is in like internet services like ads or social media. So yeah, I cannot talk about advisors recommendation. What's the role of Kafka here? Good question. So I talked a lot about like all types of happens in the recommendation system. You want to have feedback loop as quick as possible to optimize user experience. And Kafka is a solution to do this at scale. So you basically collect all the data which is produced by your system in Kafka, and then you can join these streams of data to perform to prepare training data sets. This is it. So yeah, Kafka is message management. It's not for like system messages in this case. It's for your literal like data which is produced by your users. Another important kind of bit here I think I missed is like that you don't have this scenario of technical mismatch between features in training and in serving, because you literally take feature values from serving when you prepare training examples. This is elegant solution to this problem. Okay, I don't see any more questions on recommendation systems. Let's wrap up this in last like few minutes with generative AI and self-supervised learning. You don't need a lot of examples. Probably everybody's seen like how ChatGPT works, and these examples of AI generated images. I want to talk a lot about images because I understand it much worse than text models. So, and this is going to be less about systems, because systems here are like in very early stage. So we talk more about modeling and kind of application considerations. Okay, so what are the constraints and challenges? First, obviously, enormous amounts of data and like very, very huge models as a concept. ChatGPT 3.5 had 175 billion parameters, and GPT-4 might have like trillion of parameters. This is much bigger than like number of training examples we had before. So this is very powerful models, and these models need a lot of compute to operate. You won't even fit this model into one memory of one machine typically, right? You need like distributed inference. Another difference is in inputs. In this case, you don't really have features as such. You have some form text or image, and features are basically derived from this input, similar to how we did it with embeddings for posts, speaks for words, or embeddings for like some part of image, stuff like that. So role of feature stores in a sense are kind of smaller, at least so far at this stage. Same with training data. If we are talking about self-supervised learning, when you literally don't provide training examples, but just like utilize huge amounts of text or images, you don't need to prepare training examples. We'll talk about scenarios where this is not true, but it's at least possible to train some decent model without even having like anybody prepare training examples for you. On the other hand, training is really expensive. So we haven't talked a lot about like hardware here before, but here we should say that GPU is a must. You cannot really train these models on CPU. You need a GPU. If like even in recommendation systems, you can operate with CPU machines. Here you won't be able to do it. And there are some tricks kind of for training, which could make it less or more expensive, which I talk about in the next slides. So the first one is like human in the loop. It's basically already some kind of merge between recommendation systems and generative AI. And the right part is that some examples of data used for training are human prepared, therefore like human in the loop. So for example, you can have some good responses from chat, right? And you can mark them as good. You have some bad responses from chat. You can mark them as bad. And you can also do a kind of pairwise comparison between good responses and bad, less good responses. And this is it's possible now to train like, in supervised way some smaller model on top of your large scale language model, which would greatly improve performance of your model. So the success of ChatGPT is mostly due to this, because we had large language models before ChatGPT, but they weren't as good because they weren't fine-tuned as ChatGPT is. Another example like of a trick, which in this case makes training cheaper, is low rank adaptations. This is, in this slide we have a typical like transformer architecture from Google paper from 2017. I won't go into much detail here, but what we should see here is like meters. We have two blocks of like neural networks with attention, and these blocks are repeated and could be like a lot. Each of these layers have a lot of parameters. The problem is to retrain this is like super expensive. You can spend like millions of dollars retraining this model on like real world scale data sets. But what you can do instead, if you, for example, you have some, I don't know, large language model, and you have some use case, and it doesn't perform well for use case, what you can do is you can have something called location. In simple terms, it's like set of parameters which are independent of pre-trained parameters. And new model, you freeze your pre-trained like weights of parameters and update all which you introduced as like low rank adaptation. Therefore, you like learn something new. As like a human, you learn something new by combining already and what you kind of learned from a book or from an article or from like a lecture. So this makes adaptation of models to new use cases much cheaper. And I think this is like one of the reasons of recent proliferation of these large language models, because there's some base models, and on top of this, people do a lot of interesting stuff using this approach. So not much here about systems so far. Let's talk a bit about systems. This graph is from like an article which reasons about the idea, which I tend to agree with, that we'll have like a lot of specialized AI systems on top of like this generic AI systems which we have now. It's not very likely that ChatGPT or some other model would dominate everything, because if you use it for like half an hour, you'll very quickly find some use cases where it's not really trustworthy, let's say. So to make something usable in like in real world for real business scenarios, you need to make specialized AI systems. Using approaches which we described just like on previous slides, like this lower rank adaptations is one option, or you can have some models on top of your model and specialize them by training them on like specialized examples. So I would expect like proliferation of specialized systems in near future, and probably we could, as engineers, we could participate in this. We could help to shape this landscape by defining how these systems look like, how the systems operate, how the system helps like make the world a better place. Conclude my talk on this. I'm happy to answer any remaining questions. Where in this model, chain of thoughts? Not sure I understand the questions. So chain of thoughts is kind of, it could be related to this slide. So like in large language model, what you input some text in the model, and you also have like previous outputs as it was provided by the model as inputs, and you output probabilities of next word, of next like phrase, of next sentence from the model. So this is kind of model speaking to itself. So it has some input, question sample, and start to provide some output, and we feed output back into the input. It's kind of recurrent. And model, in a sense, model thinks, model what it said, what generated already to generate new content, and arguably it's similar how humans think. So yeah, this is basically base underlying principle both of transformer and both of like previous architectures such as recurrent neural networks, that you utilize your outputs as to generate next outputs. And yeah, I would encourage to read this Google paper and maybe papers which are linked here to understand all this better. I probably not good on this to explain it in layman terms. Okay. So if you have no more questions, thank you very much for attending this talk. If you have any more questions, feel free to contact me on social networks. I'll share these slides in the chat afterwards. So thank you all and good luck. Bye.